Greetings all, Ferrariman601 here. As some of you have undoubtedly realized by this point, I am a little bit of a space geek. Yes, I know we took a look at the Saturn V a few weeks ago in commemoration of the anniversary of the launch of Apollo 11. However, today we've got something a little bit closer to our contemporary times. This, by the same company, Bandai, that made that absolutely wonderful Saturn V model, is Space Shuttle Endeavour, rendered in 1/144th scale. This is absolutely incredible. This is an extremely rare piece. It is highly sought after it was announced to be going into production starting in 2011. Collectors didn't really jump on these, though, when they came to market. Thus, they kind of sat around in warehouses and they slowly trickled out to private individuals and even museums in some cases over the years, but they are now out of production and the prices on these have absolutely soared. But what I'd like to do today is just show you in what I hope can be one of the most comprehensive reviews of this ever done on YouTube, because it is such a rare piece. I want to show you the ins and outs of the Space Shuttle, what it was, why it did what it could do, why it was an absolutely remarkable flying machine, and of course, show you the ins and outs of this absolutely wonderfully executed 1/144th scale model by Bandai. It really is an incredible piece. Once you see the engineering and attention to detail that went into this thing, you're going to be absolutely awestruck, just as I am, to be able to have something like this in the collection. So, sit down, strap in, and light the main engines, because we're going to go diving deep into the Space Shuttle Endeavour in 1/144th scale by Bandai. Talk about the Space Shuttle Program, and talk about really what makes this absolutely incredible model one of the most prestigious and one of the most highly sought after pieces in all of model collecting. Stay tuned, you will not be disappointed. Now, first off, a look at the box. Just as we did with the Saturn V, this is the box that this one comes in. It's a bit smaller than the Saturn V box because we do have fewer individual components in this particular set, but it is the same overall design, and of course it is by Bandai, so of course it is generally the same overall craftsmanship. Everything, of course, on the box for the most part, as well as all of the documentation, is in Japanese, so unfortunately, I can't exactly understand it, but there are plenty of pictures in there, so it's more or less self-explanatory, thankfully. You'll notice here on this box we do have the little add-on decal here with the Astro van and some astronaut figurines in there, also to scale with the Astro van at least. So I believe that was only included in the first edition, the first release of this production run, which I believe only amounted to 6,000 for the entire world. So it is a pretty rare piece in and of itself. We can see the dimensions here, the only bits of English that are on the box. We have 1/144th scale, so just like the Saturn V, it is the same scale. Height is about 390 millimeters, fully assembled in launch configuration. So there you go. Copyright 2010 Bandai. That's what you got here on the front side of the box. On the back side of the box, a little bit more details going on here, just showing you the different display options that you do have available. Again, everything is in Japanese, but you can just take a look at the pictures, just showing the different display options and just generally, very generally speaking here, the overall flight profile of the Space Shuttle, going from launch there in the bottom left, up through SRB, SEP, ET, SEP, and then on-orbit operations, reentry, and then runway landing. So there it is. In terms of the other panels on the box, you've got the different display options and the different configurations that you can put the model into. Looking at the orbiter, of course, the aero surfaces move, the cockpit area opens up. It's actually removable. You can see some of the interior detail there. The landing gear deploys, the speed brakes open up, the rudder articulates, and then over here you can see just all of the components that you've got in there for the orbiter and SRB, ET, stack, how the stands go together, all of that kind of good stuff. So you've got quite a few different display options available, and yeah, quite a bit of documentation on the box itself. Again,
all illegible as far as I'm concerned, because I do not at all profess to be literate to any extent in Japanese. But there it is for the box.
The Space Shuttle. What was this vehicle? What was this program? And why is it something that's worth remembering? And more importantly, why is it something that's worth commemorating in the form of this absolutely glorious model? The Space Shuttle Program. It was a manned space program that was entirely funded and executed by the United States by virtue of NASA, the National Aeronautics and Space Administration, between 1977 and 1981. The first flight of the Space Shuttle Program was on August 12, 1977, in the form of Approach and Landing Test 1-2 by the orbiter Enterprise. In total, there were 6 flight-worthy Space Shuttle orbiters built. They were Enterprise, Columbia, Challenger, Atlantis, Discovery, and Endeavour, as we see modeled here. Of those vehicles, only 5 of them were actually worthy of spaceflight. Enterprise was constructed exclusively for atmospheric test flights, as well as for use in terms of checking out procedures for how do we assemble this vehicle on the ground, how do we bring it to the launch pad, how do we transport it, and of course, how is it going to fly in the atmosphere? Because, unlike any other spacecraft before or since, the Space Shuttle returned to Earth not by parachuting down into the ocean or down to the ground in the case of Soviet and Russian spacecraft. The Space Shuttle flies back under aerodynamic lift like an airplane, and it lands on a runway just like an airplane. So Enterprise there was needed to see how this vehicle was going to perform in atmospheric flight in that very important landing phase of the mission. However, in terms of spaceflight, Columbia was the first orbiter constructed for spaceflight operations, and it made its first flight on April 12, 1981, crewed by John Young and Bob Crippen. The flight of Columbia on STS-1 was the first time, and still only time, that an American spacecraft carried a crew on its first flight in space. Nobody has tried that before or since, simply because it's really risky. For all of the American space projects that preceded Shuttle, Projects Mercury, Gemini, and Apollo, all of those initial flights were unmanned because they needed to test out the launch vehicle, the spacecraft, the control systems, everything under the sun. It was not worth risking human lives for. However, the Space Shuttle, because of the way in which it flew and how it had to be operated, it could only operate with a crew on board, at least in the early stages of the program. Therefore, those 2 intrepid souls signed on to the task of shaking down the Space Shuttle for real in space for its first ever flight, and of course, the flight of STS-1, Columbia came back entirely fine, proving the concept and then later paving the way for 135 total Space Shuttle missions. Of those 135 flights, 2 unfortunately were catastrophic failures, resulting in the loss of the crew and the vehicle. The first one on January 28, 1986, Space Shuttle Challenger, on its 10th flight, launched from Kennedy Space Center, as did all of the Space Shuttle missions. 73 seconds into the flight, a failure on one of the solid rocket boosters resulted in a structural breakup of the external tank and orbiter, unfortunately leading to the loss of the crew and the loss of the orbiter Challenger. In 2003, Space Shuttle Columbia, the first shuttle to fly, coming back after a marathon 16-day flight. It was re-entering the Earth's atmosphere on its way to a scheduled landing at the Kennedy Space Center in Florida. Structural damage that was sustained on liftoff on the orbiter's left wing allowed hot atmospheric gases to enter into the orbiter, getting past the thermal insulation on the outside that we'll talk about later on, and it effectively melted the relatively lightweight and thin and totally not heat-tolerant aluminum airframe of the orbiter, unfortunately resulting in a structural breakup of the orbiter and the loss of the crew. For these reasons, and some more that we'll get into, the Space Shuttle ultimately was deemed to be a project that was too costly, not only in terms of the human lives that unfortunately were lost along the way, but also in terms of monetary cost. The Space Shuttle Program was an incredibly expensive endeavor. Typically, a launch cost about $1 billion in 2011 dollars. So for a single flight, you needed at least $1 billion to get this thing off the ground and for it to do its mission. Eventually, the country decided, no, this is not a worthwhile pursuit anymore, and we're just going to stop this whole program. Unfortunately, we don't fly the Space Shuttle anymore. The last Space Shuttle flight was in 2011, flown by the orbiter Atlantis. That sealed the deal on 30 years of space exploration courtesy of the Space Shuttle, and still to this day, the Space Shuttle has yet to be succeeded in terms of American manned spaceflight. We do still send humans into space, courtesy of Russia and their Soyuz system, which has been flying itself since the 1960s, very reliably as well. But we do have some newcomers to the space business. Most notably, SpaceX and Elon Musk are testing vehicles. They've had much success with them already in terms of putting unmanned payloads into orbit and also sending them out on what could be interplanetary trajectories. But manned spaceflight from North America is no longer possible today in 2019. Hopefully, in the future, with development of new launch vehicles and new spacecraft, NASA will be launching American crews from the United States again, but we're still at least a few years away from all of that. Therefore, the Space Shuttle still represents the pinnacle of American technology when it comes to spaceflight. Before we go on, we need to establish some terminology and some nomenclature here. The Space Shuttle stack, as it's called, as we see it here, this is how the Space Shuttle was configured for liftoff and for the first 2 minutes of flight. The constituent parts of the Space Shuttle stack were as follows. Here, the white airplane-looking section, this was the orbiter. As we mentioned, there were 6 orbiters that were built for the Space Shuttle program. This one, Endeavour, was the last one constructed. It was the newest. Endeavour first flew in 1992, and it made its last flight in 2011. The large orange cylindrical structure that we can see here, this is the external tank, or the external fuel tank. What it is, it's a big fuel tank. The Space Shuttle main engines, which we'll take a look at later on, take their fuel from that external tank. It is loaded with liquid hydrogen in the lower section and liquid oxygen in the upper section. The remaining components of the Space Shuttle stack were 2 solid rocket boosters. Those are these cylindrical white devices on either side of the external tank, the left-hand solid rocket booster visible here. Those were big, powerful, solid propellant engines that gave the Space Shuttle about 80% of its total thrust at liftoff, and liftoff was not possible without the use of those solid rocket boosters. They burned for the first 2 minutes and 5 seconds of flight, after which time they were jettisoned and they fell away into the ocean. This is also a nice segue for the other groundbreaking part of the Space Shuttle program. In addition to being able to come back and land on a runway more or less like a conventional aircraft, the Space Shuttle was also designed to be the world's first reusable space vehicle. Up until this point, every launch system that we had, whether it be for Project Mercury, Gemini, Apollo, or for the Russians with their Vostok, Voskhod, and Soyuz programs, the launch vehicles and the spacecraft were built for one flight and one flight only. The booster components had to be discarded immediately after they had expended all of their fuel, and they either crashed into the ocean, or in the case of the Russian programs, in remote areas of land, or they burned up in the atmosphere if they were jettisoned farther along into the launch profile. Same is true for the American systems. They burned up in the atmosphere or crashed into the ocean. However, the Space Shuttle was different. The Space Shuttle was meant to be used multiple times, and those 135 flights all being made by 5 space-worthy orbiters in the course of 30 years. That's why the orbiters were reusable. As well,
were the solid rocket boosters that we see there. They would be jettisoned about 2 minutes after launch. They would fall into the ocean under parachute. They'd be recovered by ships stationed in the general vicinity of where they'd be expected to land, and then they would be towed back to Cape Canaveral, cleaned up, repaired if necessary, then reloaded with more fuel, and then used on the next launch. The external tank, though, the largest single component of the shuttle stack, well, that had to be attached to the orbiter until it was more or less in orbit. Therefore, the overall velocity that the vehicle has accrued by the time it's in orbit is really, really high, about 17,500 miles an hour. The external tank, largely made out of aluminum and other lightweight materials, was not able to withstand the forces of atmospheric reentry. It had no mode of being recovered, therefore the external tank would burn up in the atmosphere after its one and only launch. So out of the four major components of the space shuttle stack here, the two solid rocket boosters, the orbiter, and the external tank, the largest one, not reusable. So there you go with some of the cost already with this system. However, the rest of it, solid rocket boosters, they could be reused around up to 10 times, and the orbiter, of course, was theoretically reusable for an indefinite number of times, although by the time we got to 2011, and at that time the three remaining orbiters were all over 25 years old, it was definitely starting to show some signs of aging on all of the orbiters that NASA still had at that point. So perhaps not a perfect system. It certainly was not a perfect system, and we'll get into some of that later on. But again, there's just the overall nomenclature of how all of this works. We have the orbiter, the external tank, and the two solid rocket boosters as we see there. And again, going back to our initial view with all of that, there is Endeavour in all of its absolute resplendence. Now, the overall flight profile of the space shuttle was as follows. Unlike other vehicles before it that were designed to leave the general vicinity of the Earth, in the case of the Saturn V, to go to the moon and land on the moon, the space shuttle did not have quite that capacity in terms of the actual distance that it could travel. The space shuttle was designed to fly in the domain of low Earth orbit. However, in exchange for being able to fly to the moon per se, the space shuttle gained an absolutely colossal payload capacity. I believe the overall capacities for the space shuttle were something on the order of 35,000 pounds to low Earth orbit. So by low Earth orbit we mean around 200 kilometers or so in altitude. So it has a pretty significant payload capacity. The Space Shuttle also had, and we'll take a very close look at this later on, the Space Shuttle also had a very large payload bay. So in terms of all of this, yes, you lose some of the prestige of being able to go to the moon per se, but you also gain the capacity to do a lot of really interesting things in return. For example, some of the payloads that were launched by the Space Shuttle include the Ulysses spacecraft that eventually explored Jupiter and gave us a whole bunch of data back, many communication satellites, many projects for the Department of Defense, and probably most prestigiously, the Hubble Space Telescope, and very large and very important components for the International Space Station. In fact, the first assembly flight for the International Space Station launched on December 3rd, 1998, and it was actually flown by Endeavour. It carried the Unity module up into low Earth orbit, which rendezvoused with the Russian Zarya module, which was launched about a month earlier, and the International Space Station was born when those two vehicles, those two modules, docked in low Earth orbit courtesy of Space Shuttle Endeavour. And the International Space Station, as of 2019, is now complete, and it is still flying today, and it has been continuously crewed, I believe, since the year 2000. So we've got 19 years of continuous human spaceflight, and all of that pretty much was only achievable because of the Space Shuttle. Let's get into some of the technical specifications on the vehicle, and then we'll show you the flight profile. The Space Shuttle stack, as you see it here, this was the configuration during vehicle assembly, transport to the launch pad, launch, and then for the first 2 minutes or so of flight. There were a number of different manufacturers and vendors who collaborated to build the vehicles for the Space Shuttle program. The solid rocket boosters, 2 of which you see here, and that's the nominal configuration for launch, they were built by Morton Thiokol, later on becoming the United Space Alliance and Alliant Tech Systems. The external tank, the large orange structure here that we see, that was designed and built by Lockheed Martin, earlier on Martin Marietta becoming Lockheed Martin. And then for the orbiter, all 6 orbiters that were built for flight use, 5 of them for use in space, they were constructed by Rockwell and they were later absorbed into Boeing. So we've got multiple different companies, multiple different industries really as well collaborating for the Space Shuttle program. Obviously you've got the aerospace industry, but you've got all sorts of innovations going on in material sciences, computers, hydraulic systems, all kinds of things that were necessary to make these vehicles work. So there were many people involved in the design, construction, and operation of the Space Shuttle, even for a single flight, never mind a 30-year program of spaceflight. So you've got a lot of complexity going on already just in the overall configuration of this thing. As we mentioned, this was a very expensive program. The overall project cost was about $209 billion in 2010 dollars. The cost per launch, depending on the configuration, how much payload were we putting on board, how many people were going on board, that could range from anywhere in 2011 dollars to $450 million to $1.5 billion per flight. So this is a very expensive thing. The overall configuration, as we see it here on launch, the height was 56.1 meters, or 184 feet 1 inch, so that is the height of the external tank here, tilted vertically for launch. The overall diameter of the external tank, 28 feet 7 inches, or 8.7 meters. The overall mass at liftoff, 4,470,000 pounds, or 2,030,000 kilograms. So we've got ourselves a very heavy vehicle. Again, not quite as heavy as the Saturn V on launch, but still a monumentally large thing that has to be shot up off the ground and then later into orbit. Capacities here. Now, the orbiter, in terms of its capabilities, and really the overall stack in terms of its capabilities, is somewhat limited compared to something like the Saturn V. We were going to the moon before the Space Shuttle program. The Space Shuttle is designed for flight in low Earth orbit, really. So we're not going to the moon. We don't have that distance capacity anymore, but what do we gain from it? Well, we gain the capacity to loft some very heavy materials into low Earth orbit, which enables us to do some really interesting things. For example, the payload capacity to low Earth orbit was about 60,600 pounds, or 27,500 kilograms. Payload to the International Space Station, which is a program that probably would not have been possible without the assistance of the Space Shuttle, was 35,380 pounds, or 16,050 kilograms. Payload to geostationary orbit, that was 8,400 pounds, or 3,810 kilograms, and that of course was going to involve some upper stages on the payload itself to be able to get to those higher altitudes. Polar orbit, they could get 28,000 pounds or 12,700 kilograms into polar orbit, and they could also return to Earth, a payload capacity of 31,700 pounds or 14,400 pounds. So you've got the capacity here in exchange for being able to go far distances, like to the moon, for example. You now have the capacity to bring very large single objects into orbit, which then enabled NASA to do some pretty interesting things. Of course, the International Space Station is still flying today, continuous human presence in space since the year 2000, I think. You had the Hubble Space Telescope, launched in 1990, still up there, still operating today. So you understand that for the trade-off of losing a lot of the distance capability, being able to visit places like the moon or maybe sending things out on interplanetary trajectories, in exchange, you get the capacity to build things in space, namely the space station. So the space station that exists today exists pretty much entirely thanks to the space shuttle. Now, you could argue, okay, perhaps a space station isn't quite as exciting as going to the moon, and I tend to agree with that. But the amount of science and the amount of innovation that can happen in space when you have a place that people can go to that's reasonably safe, that's very well known, something that's going to be consistent, something that doesn't have to rely on continuous ground support in terms of constant resupply, constant monitoring in terms of making sure that you're going to be able to make it back to Earth okay, you can start to focus more on the scientific aspects of spaceflight. You can also put people into space for much longer durations than you could on single launch missions. Therefore, you can study what happens to the human body for long durations in space. I believe the record for the longest spaceflight is something on the order of 16 months, something like that. So eventually, if we want to return to places like the moon, or if we want to extend our reach out into the solar system a bit further, maybe wanting to go to Mars, or maybe wanting to rendezvous with an asteroid someplace and try to land there, these are flights that are going to take many months, if not years, to accomplish given current technology. So a vehicle like the Space Shuttle enabled us to put people into space long term and to discover what happens to the human body and the human mind when you are in that environment for a considerable length of time. What happens to the body? What happens to your muscles? What happens to the heart when you don't have to be burdened by gravity, when the heart doesn't have to constantly pump against gravity trying to pull all the blood down? What happens to the brain? What happens to people who are isolated from the rest of humanity for that amount of time? Can we survive radiation exposure? There are all kinds of questions that come to the surface when we have the prospect of being able to stay in space for months and months, if not years at a time. And these are all problems that eventually are going to have to be solved if we're going to extend our reach beyond the Earth and the Moon. So for that, the Space Shuttle was absolutely indispensable, and it was the only vehicle that could do these things. It enabled us to build a space station. In terms of astronomy, it lofted two of the heaviest payloads ever launched into space, the Hubble Space Telescope and the Chandra X-ray Observatory. Both of those spacecraft are still operating today. Hubble, of course, needs no introduction. It's brought back some of the most breathtaking images ever. The Chandra X-ray Observatory, same sort of thing, but shooting in the X-ray spectrum rather than the visual spectrum like Hubble mostly does. It's done a lot of research on black holes and quasars and star formation, all kinds of things, and all sorts of questions that, again, we're going to have to understand the answers to if we're going to survive long-term as a species. So perhaps you don't have the prestige of the one-time event of going to the moon. Perhaps you don't have the prestige of being able to send people on a Mars flyby, but the Space Shuttle, it's a little bit of a clunky, even ugly sort of vehicle, but it was able to do some really interesting things. And more importantly, it put us in a position now to have another 30 years of spaceflight experience, to have more questions that need to be solved, but to have answers to many of the questions that we had beforehand in the Apollo era. Now it puts us in a position to be able to put the human development side and the technical development side together and perhaps return to the moon, or perhaps go off to Mars. So as much as people really, in some cases, pick on the Space Shuttle program, I think it definitely had a purpose, and it served it pretty well. All right, so total installed power. As we've talked about, we have the two solid rocket boosters on either side of the external tank, and then at the base of the orbiter, not quite visible here, there are three main engines. The Space Shuttle main engine, SSME for short. Three of them down here, supplemented by the two solid rocket boosters at liftoff. The Space Shuttle main engines, they were liquid fuel. They ran on hydrogen and oxygen from the external tank here. And at liftoff, all three main engines and the two solid rocket boosters would fire. The three main engines, they are producing a net thrust of 1,180,000 pounds at sea level. That's 5,250 kilonewtons. The main engines had a burn time of 480 seconds, a specific impulse of 455 seconds, which enabled the vehicle to gain a total of 4.46 kilometers per second of speed. The solid rocket boosters here, they of course both fired simultaneously. They had a total thrust at sea level of 2,800,000 pounds or 12,500 kilonewtons at liftoff. They had a specific impulse of 269 seconds for a net speed gain of 2.64 kilometers per second. They burned for 124 seconds, so that is 2 minutes and 4 seconds of flight time. The general launch sequence for the space shuttle, it was really a multi-day affair in terms of getting everything ready to fly. First off, months before launch, the vehicle would be assembled in the absolutely enormous Vehicle Assembly Building at Kennedy Space Center. If you've never been there, you must go there. It is, I believe, still the second largest building in the world in terms of interior volume. The whole stack would be configured in there, and it would be assembled on a mobile launch platform. Unfortunately, the display stand that we have here is not really representative of what the actual launch pad looked like, but the space shuttle would be assembled in there, and then it would be rolled out to the launch pad vertically on a crawler system. The same crawler transporters and the overall same mobile launch platform that was used for the Apollo program, transporting the Saturn 1B and Saturn 5 vehicles to Launch Complex 39 at the Kennedy Space Center. Tanking, or fueling, of the external tank would be started about 12 hours or so before the planned launch time. The solid rocket boosters, they came to the Kennedy Space Center already loaded with their solid propellant. So that is 100% storable propellant. It could basically sit there indefinitely as far as they're concerned. But they start loading the liquid oxygen and liquid hydrogen into the external tank about 12 hours before launch. And of course, all this is facilitated by a rather large launch gantry system that would be sitting to the left of the vehicle. Unfortunately, not pictured here, but that would be a cool model to have. Anyway, the crew would enter the vehicle through a hatch on the side, which we'll see later. Up to 7 astronauts on a nominal flight would be inside the space shuttle. The vehicle had a nominal capacity of 8, and it could even support 11 astronauts in an emergency situation. Say they needed to evacuate the space station, and the space shuttle just happened to be there. But typically we saw crews of 7. I believe the largest ever crew was 8, but no more than that. The first space shuttle flight only took 2 astronauts, and on many flights you would see 4 or 5, but maximum typical capacity was 7 astronauts. They would enter the vehicle, the countdown would proceed. The launch sequence went a little bit something like this. At about 5 minutes before flight, the vehicle would start to transfer its power management from the ground to the onboard systems. The space shuttle had a pretty sophisticated power generation system. It had 3 auxiliary power units, much like you would see on an aircraft today. These were small turbine units that ran on hydrazine, the same fuel as the reaction control system on board the space shuttle, the little maneuvering engines for changing the attitude in space. They would start up at 5 minutes before the launch, and the vehicle would start to run on internal power from the auxiliary power units providing hydraulic pressure and electrical power, as well as fuel cells that were burning hydrogen and oxygen in there, producing most of the electrical power for the onboard systems, the avionics, life support, things like that. At 30 seconds before launch, something called the ground launch sequencer, this was a computer program, would take over, and that would actually run the whole launch proceedings from the pad. 15 seconds before the launch, something called the sound suppression water system would kick on. And what this was a big water tank about 800 feet to the east of the launch pad that would just dump thousands of gallons of water onto the launch pad and below the vehicle in the flame trench area of the launch pad. It wasn't so much there to keep things cool on the ground as much as it was there to suppress the sound, hence the name sound suppression system. The amount of noise that a vehicle like this could produce on launch would be well enough to cause structural damage to itself. Therefore, NASA needed some way to avoid that happening. So they figured, hey, water is plentiful and it's pretty good at absorbing sound, so there you go, the sound suppression water system. 10 seconds before launch, on many videos, actually pretty much all of them, you will see that there will be sparks that are sprayed around the base of the orbiter in the vicinity of the main engines. Those didn't ignite the engines. What they did was they would serve to ignite any residual clouds of hydrogen gas that could have been around the engines there, because they didn't want any explosions going on here prematurely. So you'll see sparks firing around the base of the main engines, and then at 6.6 seconds, the main engines are ignited on the tail of the orbiter. They ignite in sequence, engines 1, 2, and 3. So the right-hand engine, the left-hand engine, and then the center engine all come up to power, slightly staggered, so you could actually see that in some of the videos. They run up to full thrust, and you'll notice on many of these videos it's evident, because the main engines are mounted where they are, and because the orbiter is mounted on the side of the center of mass of the vehicle here, the external tank, the largest and heaviest single object here in the stack, when the main engines are coming up to full thrust, you actually see the entire vehicle start to tilt over a little bit as the main engines are firing. That was called the twang, and it was completely normal. It was something they accounted for even early on in the design phase. And yeah, we saw the vehicle start to tilt over on itself, and then it came back to vertical. When it came back to vertical at T0, the two solid rocket boosters would be ignited. When those solid rocket boosters ignited, they immediately are at full power, and because the entire stack, the main engines and the solid rocket boosters combined, are producing more thrust than the vehicle physically weighs, you then have liftoff. And liftoff on the space shuttle happened pretty fast. It was not like it was on the Saturn V, where you had this sort of slow, lumbering, quite majestic-looking spectacle coming away from the launch pad. On the space shuttle, it happened really fast. 0.3 of a second was all it took for the space shuttle to leave the launch pad and start that initial part of its climb. So it happened pretty fast. There's a lot of power going on in this moment. So at this point, you can see the engine configuration here. The main engines on the base of the orbiter, the three of them there, and the two solid rocket boosters are firing. The thing about the solid rocket boosters is, because they're solid propellant, you can't turn them off once they're lit. Nor can you throttle them, really. So once the solids are lit, you're going. There was no turning back. The main engines, they could be shut down at any time. And they were also very highly throttleable. So if you got to a point in the launch where all of a sudden things were not going so well, you could shut the engines off before the solid rocket boosters were ignited. And this actually happened a handful of times and caused no real ill effects. But once the solid rocket boosters lit, they were committed and they were flying. After launch, the vehicle leaves the launch pad and clears the tower. On all of the flights, you'll see the space shuttle go into a very dramatic roll. And what this did was it put the vehicle on the proper heading for ultimately where it wanted to end up in terms of going into orbit. Now, it's pretty difficult for me to maneuver this thing around because it's actually quite heavy. But you'll see on pretty much every launch video, depending on the angle you're looking at, you'll be able to see the whole vehicle roll over and then start to pitch over as it's climbing away. So the space shuttle had a very interesting launch sequence and initial few seconds of flight as it's starting to find its trajectory. So it's pretty dramatic to see, and definitely very cool as well. The space shuttle ultimately, during launch, it would settle into what they called a heads-down position. So the vehicle would be pointing the cockpit area toward the ground as you're going up. And this was basically to put the vehicle into the optimal aerodynamic configuration for the first couple of minutes of flight. Because, of course, you're low in the atmosphere and you're starting to gain speed really, really fast. About 40 seconds after launch, the vehicle is going to exceed the speed of sound. So they're getting up to about 700-800 miles an hour at that point. In launch commentaries at this point, you'll also hear the term maximum dynamic pressure, or max Q. What this is because they're getting through Mach 1, the speed of sound, the aerodynamic stresses on the vehicle were at their highest at that point. So what they did to counter this a little bit, remember you can't really control the output of the solid rocket boosters, but what they would do is they would throttle the main engines down through about 65% of total rated thrust. And what that did was it lowered the rate of acceleration a little bit, and it just sort of allowed the vehicle to hang out as it went through the higher density areas of the atmosphere. Once it got to about 65, 70 seconds into the flight, the main engines would be throttled back up to their maximum nominal operating capacity, which was actually 104% of thrust. When they did the performance benchmarking on those engines in the late 70s, they figured out what the operational envelope was, and then they started to update the engines a little bit, and they realized that they could actually make them run a little bit higher, and they just didn't bother to redo their data tables, so they called it greater than 100%. But that's what they did. So, shuttle flying in this configuration overall for the first 2 minutes and 5 seconds of flight. When you got to 2 minutes and 5 seconds, you had to get rid of the solid rocket boosters because they're out of fuel, and well, it's dead weight at this point. So we got to get rid of the solids. They're useless, and they're just becoming a little bit of a hindrance by this point. So we've got to get rid of them, and to do that, we need a jump cut. So we're flying out. The solid rocket boosters have burned out. We are about 150,000 feet in altitude, and we're traveling at about 3,500 miles an hour. Solid rocket boosters are out of fuel. We have to ditch them. Solid rocket boosters are attached to the external tank by two principal struts, one forward and one aft. We'll take a better look at them later on, but you can see the aft struts here on the solid rocket boosters on either side of the external tank. So to ditch the solids, explosive bolts would blow, retro rockets would fire, and then the solid rocket boosters would fly off unpowered, and they would just fall back down. Go to the second booster. So there you go. In this configuration now, the space shuttle would still be flying heads down, they called it. So it would still be inverted relative to the ground, and it would continue to fly uphill like so. And this would continue all the way up to 8 minutes and 30 seconds. At this point, the vehicle will pretty much have achieved orbital velocity, again, which is about 17,500 miles an hour, and the main engines then will have exhausted all the fuel remaining in the external tank. On later flights, they actually would have rolled back up to a heads-up position. This was after many space shuttle flights, coincidentally, to put satellites into space to relay communication. So on the flights where they ran the external tank camera, where you could actually follow the whole flight from on board all the way up through main engine cutoff, you'll see them separate in a heads-up orientation. But on the early flights, they would have been heads down, facing the ground like that. But regardless, 8.5 minutes into the flight, the main engines have expended all the fuel in the external tank, so they shut down at about 8.5 minutes in, and then it's time to remove the orbiter from the external tank. The orbiter is attached to the external tank by two principal struts, one here forward that we can see, and then one aft that we can see here. So we see we detach from the external tank, we pull the orbiter free, which is a little bit difficult to do. There we go. And then the external tank is left to re-enter the atmosphere eventually. It's basically in orbit in its own right, so it will take several days in some cases to come back to Earth, but eventually it does go back to Earth, and it burns up in the atmosphere. Some pieces of it make it to the ground or the ocean, but they try to make sure it re-enters over the ocean, but again, there it is. So at this point, our orbiter is now in orbit, thus living up to its name. But we're not quite in a stable orbit yet. At this point, just using the velocity of the main engines, we will come back to Earth at some point. We will have our orbit decay eventually. Usually within the space of a few hours, we'd make it around the Earth a few times, and then we would just fall back in. Because remember, we're in low orbit, so there's still a little bit of atmospheric drag where the space shuttle is flying. So what did we do about that? On the tail section of the orbiter, we have two additional engines. We have these two, the orbital maneuvering engines on this side. The main engines are now completely out of fuel. They will not be used again until the next launch. But we do have these orbital maneuvering engines. I believe these were AJ-10 engines, same used on satellites still today. And these ran on hydrazine and nitrogen tetroxide oxidizer. Same fuel as the RCS thrusters. And these would fire to give us the last little bit of kick we needed to get into orbit. So once we're in orbit, the space shuttle flies more or less in this configuration here. We just have the orbiter now, and we're on our own. We have transitioned from being a rocket to a spaceship, and there it is. Alright, so we have ridden the solid rocket boosters and main engines into orbit. We fired our orbital maneuvering engines, and we are now in a safe and stable orbit that's going to be there for as long as we need to accomplish our flight. Now, it depends greatly what happens next in terms of what the actual objectives of a given flight were. In terms of the first few flights of the space shuttle, it was just to test the vehicle itself. Will it launch? Will it stay in space? Will it come back? Later on, once they had proven that the vehicle was flight worthy, then they started to use that big cargo capacity of the space shuttle to great effect. And some early payloads of the space shuttle were things like the Space Lab, which enabled kind of a space station type environment just on board the shuttle. It was an extra module that they could put inside the payload bay, and that enabled them to do all sorts of things. There was a package that was installed in some orbiters for long duration flights, being able to stay in space for up to 31 days if they really wanted to. The longest shuttle flight, I believe, was 16 days. That was done a couple of times. But they had the capacity just to have a self-contained orbiter up there for a month, which was pretty cool. Other things, we mentioned the Ulysses spacecraft, the Galileo spacecraft, all sorts of communication satellites, the LDEF, the Long Duration Exposure Facility, all sorts of early space shuttle payloads that did all sorts of really cool things. Later on, the space shuttle could dock with the Mir space station when it was still up there. They eventually deorbited Mir in 2000. Construction of the International Space Station, all kinds of really interesting and innovative things that were done by the space shuttle. However, as far as we're concerned on our flight, the next thing that we must do is to open the payload bay doors. Because not only did these provide access to the very large cargo bay on the orbiter, but they also contained radiators that were very important for making sure that all the systems on board stayed cool enough so that they wouldn't have equipment failures later on. So we must open the payload bay doors. Now here on the model, this is accomplished by opening up a couple of hinges here. We can see one here and then one right here. What we have to do is pop these up initially. There we go, on one. And then the other is mostly popped open in its own accord. So we do that. Then you reach over and you pop it open like so. The other one then will pop open with a little bit of persuasion. And there it is. We now have our cargo bay open, and you can see that we have got some cool stuff inside. So, inside the payload bay of Endeavour here, it's empty for the moment. There are a couple of payload accessories that we can put inside if we want to. We'll show you those a little bit later on. But first of all, what we have here is the shuttle's remote manipulator system. Robotic arm. This was a 50-foot arm, and because we know that this is 50 feet long, you can get a sense of the dimensions of the orbiter here. This, in the model, is completely articulated, and it stows on a little pin there on the port side aft of the vehicle, and then, you can see, it's completely articulated. It bends at the elbow and wrist joint there. It's very nice. You can swivel it around 360 degrees, and you can even grapple objects with it. But that is the robotic arm. I believe this made its first flight on shuttle on STS-2, the second space shuttle flight. And as you can see there by the branding on the side of the arm, it was put together on behalf of the Canadian Space Agency. So some Canadian involvement in the Space Shuttle Program as well. Very cool. So that's the robotic arm. This enabled the Space Shuttle to do the vast majority of the cool things that it was able to do in flight, because with this, you now have a reach. You can extend your dexterity, basically, out around a perimeter of the vehicle, and you can manipulate objects. You can manipulate payloads. You can retrieve satellites from orbit with this device, and they did on many occasions. You can deploy things. You can grab things from inside your own cargo bay with this, and then you can set them off, and you could orient them however you need them, and then you could release them and send them on their way into their own orbits. All sorts of great capacity happened because they had the ability to put something like this in a spacecraft so large, because now all of a sudden you're not bound by basically just having a small little capsule set up. Now you've got a real workspace on orbit. The other device here that you can see, also with the Canada branding on it, this is the boom extension to the robotic arm. And what this actually was something that was implemented on later shuttle flights for the purposes of inspecting the vehicle. We'll get into this when we get to talking about reentry. But what this was a sensor array. And this had cameras on it and infrared and ultrasound sensors that could be used to inspect the orbiter in flight. We mentioned the Columbia disaster, the loss of Space Shuttle Columbia in 2003 at the top of all of this. The reason why Columbia was lost was because there was damage to the airframe and the thermal protection system. They didn't have the capacity on Columbia to inspect the integrity of the heat shield. Therefore, this was added on all subsequent flights, and procedures were introduced to use this boom to be able to inspect the orbiter on orbit, in flight, and therefore they could determine whether or not there was any damage to the vehicle itself. I'm just trying to include this in here. This may require a jump cut. Yes, it will. So yes, now you've got the robotic arm extended, you've got the boom extension affixed, so now you can just visually see that your reach around the vehicle has increased exponentially. So you can basically now access every portion on the orbiter just so that you could get a visual on everything that could potentially have sustained damage on launch, just making sure that everything is in fact okay and ready to proceed with re-entry at some point. But there it is, boom extension, and ultimately that gives you about 100-foot radius that you could reach around. So that is almost the entire footprint of the vehicle, which is really, really cool to see all of that. So there it is. You get underneath if you need to, check the trailing edges of the wings, where the elevons are, the tail section, all of that stuff. So it's really cool, and again, having that arm there really does give you a whole lot more flexibility and versatility in terms of the sorts of scenarios you can get yourself into. Stow the arm now. Let's put that down. It locks in on its own little pin arrangement there. There you go. Just collapse all the joints down. And we'll take a little bit more of a look inside the cargo bay now that we're not playing with things anymore. Here it is, just empty, and you can see that there is a lot of space. It is a concave, hollowed out cavity inside the midsection of the orbiter. And it's pretty large. It's roughly equivalent to the volume of a standard American railway boxcar. So you could get a lot of stuff in here. Details that we can see here are the rear windows overlooking the payload bay from the cockpit. this silver circular device. This is actually a docking adapter so that the space shuttle could dock to the International Space Station. Pretty cool. Below that is the airlock that leads into the mid-deck, 2 levels on the space shuttle, and that enabled the crew to access the payload bay. So they could go out on a spacewalk and access the payload bay and do whatever was necessary to do out there. Beyond that, you can see this is an antenna array, which actually is deployable. Gotta move the arm out of the way there. There we go. So that is a communications antenna, and of course that is important for making sure that the ground has good communications with them and good tracking data as well. So really, the space shuttle would fly around in orbit like this with the payload bay doors open. Remember, there's effectively no air resistance up here. There's basically no appreciable atmosphere, so don't worry so much about aerodynamics and all that stuff. So it's all very nice. And again, the radiators, which we've got some decent detail of here. The forward half of the doors in reality would have had a deployable radiator segment that would just sort of lift up from the door skin. Not included on this model, but they did give you some pretty nice silver detailing there as a compromise. So that's pretty nicely put together, I must say. And again, it just gives you a decent idea of what this would look like. So that's the inside of the payload bay. I mentioned that we actually have some payloads that we can load into the payload bay, and here they be. This first one, this is some sort of a sensor array, something like that, something that would remain in the payload bay for flight, I do believe. But you can see that you can place these items down into the payload bay if you so desire. They kind of fit in there. They do fit. It's a little bit tricky to get them properly mated in there, but they do fit inside, and you can kind of basically put them wherever you want in terms of how you'd want to display this. But yeah, they would go in there. Probably the much more interesting one, though, has got to be this. This is one of the multi-purpose logistics modules that would be used for the space station as either as a resupply module or just a temporary structure that they could put on there, basically wherever it was needed. And again, that also would fit inside the cargo bay, much like this. So you can see how generally how you could have things inside the cargo bay. Again, the doors won't close with that in there, at least not in that configuration, but there it is, and it's all pretty cool to see. And again, you get to be a little kid again and play with this kind of stuff and determine, okay, what sort of payload configuration am I going to have on this thing, you know. But it's just cool, and it's really cool to see that they went through the trouble of actually making an authentic looking thing to put into the cargo bay, just in case you want to display it like that. You could also, of course, manipulate that with the robotic arm and all that kind of stuff, but I won't bore you even more with all of that stuff going on. But again, it is pretty cool to see all that. Additionally, you have 2 scale astronauts in their EVA suits, their extravehicular suits, able to go outside there. There they are. They are utterly minuscule. They are also in 1/144th scales. There they are. And you could just get the sense of how tiny a person is in comparison to the space shuttle. Here's somebody, oh, that's not going to work. Remember, there's no gravity when these guys would be out there. But there's generally your comparison of how small an average size human would look in the payload bay of the space shuttle. So this thing is pretty big, as you can tell. But yeah, that's cool. And the astronauts, they also they have little pegs here in their packs, their oxygen packs in the back, where you could actually set them up on included little flexible stays where you could have them displayed if you really wanted. But I don't know. There's just yeah, they don't stand up on their own too well. They're just, the center of gravity is completely messed up. But that's what they are, and they're really tiny, and but the detail on them is really cool. And yeah, there you go. Face shield in the gold foil, as it would really be. The red stripes on the pants section of the suit. Some detail there on the front section of the controls and valves, but nothing really to write home about. But it's a cool thing that they included that there. But yeah, that's pretty cool. At some point, though, when your flight is over, you've accomplished your missions, you've got to go back home. So what does that all look like? First thing that we need to do if we're going to be going home anytime soon is to close the payload bay door. So we stow our communications antenna, and then we close our bay doors like so. Like that. They will meet up. There we go. We kind of get the left door situated first, and then the right door will kind of fall into line with it, and then everything will close up. Very nice. Next thing that we have to do is we have to maneuver this thing into a retrograde attitude, which means that we need to be flipping around backwards to our direction of travel. So we do that, and then the two orbital maneuvering engines that we talked about earlier, the two smaller engines that are toward the bottom of the screen here, these will light up on that retrograde attitude, and they will burn at a specific time, in a specific place, for a specific duration, and then that will slow our velocity down so that we start to fall out of orbit. And because the space shuttle is in low Earth orbit, and even though it doesn't really have much fuel left at this point, the main engines that fired on launch don't have any more fuel, the total speed of the vehicle only needs to decrease by about 200 miles an hour so that it starts to fall down out of orbit and that it will re-enter the atmosphere on its next pass around the Earth. So they really did a good job with limited resources once launch was done and most of your fuel was gone. And again, really the only difference between staying in orbit for a considerable length of time and coming back on the next pass was a couple hundred miles an hour. Pretty cool. Because remember, we're doing 17,500 give or take, and the difference there of being 200 or so miles an hour, that's pretty profound. But we're still going pretty fast, and we have a lot of speed to bleed off if we want to come to a stop on a runway at a destination near you. So how does that happen? So in order to slow down from near orbital speeds to eventually zero on the tarmac at hopefully Kennedy Space Center or Edwards Air Force Base, the two prime landing sites for the space shuttle. A third one was used, White Sands Missile Range in New Mexico. STS-3 landed there, and then that was the only time the space shuttle landed there, Columbia, on that flight. But as we start to get lower toward the atmosphere, what we're going to do is we're going to start to transition from being a spacecraft to an aircraft. So in order to bleed off as much speed as we possibly can, what we need to do is we need to face forward again, and then we need to start pitching up to about 40 degrees relative to our velocity vector. So that is the direction and angle at which we're flying. So we will pitch up, and in so doing, we expose the belly of the orbiter to the onrushing airstream. And remember, because we're traveling so fast, we get into some pretty expansive and extensive heating regimens going on. Just like we talked about in the Saturn V review, we're running into the atmosphere at appreciable speed, and that generates a lot of heat. So how do we counter that? Well, on Apollo, we had a heat shield that could burn up because we were only going to be using that vehicle once. But on the space shuttle, we have a different problem. This vehicle needs to be reusable. It needs to fly multiple times. So we can't have a heat shield that's designed to just burn away. So what did NASA do? They came up with a pretty ingenious system using tiles. There were tens of thousands of silica tiles which lined the entire orbiter, and they were most important on the belly of the orbiter here where you see this black section. Generally speaking, as far as the colors go, the black areas on the vehicle got the hottest. So you notice there's a lot of black around the nose, the leading edges of the initial strakes of the wings, and then the entire belly of the orbiter is black. And the reason for that is these tiles, by themselves, they could withstand heating of around 2,000 degrees. So the white sections there, they are good for about 2,000 degrees. But the black sections had an additional 1,000 degrees of heat capacity. So about 3,000 degrees in total for the black sections of tiles and about 2,000 degrees for the white sections of tiles. these tiles, and I actually used to have one. They're very cool. They are extremely light. They're made of silica fibers, but the majority of the compound is actually made of air. It's just empty, void air space. And what that enables it to do is the silica is very heat resistant and very heat resilient, but the air acts as an insulator that keeps that heat from being transferred to the underbody of the orbiter. The airframe is just made of aluminum, remember. So you have the very heat resistant silica fibers in the tile, and then you also have air voids, which will serve to just insulate everything and keep the heat from being transferred to the aluminum airframe. So it worked very nicely. The downfall of the tile system, though, was they were extremely light because they were extremely not dense. They were mostly air, again, as I mentioned. But that also meant that they were very fragile. So any sort of impact to the tile could cause significant damage, and it could cause the vehicle not to make it home, which unfortunately is what happened to Columbia in 2003. For Columbia, it was even more critical, though, because there are a lot of tiles on the space shuttle, and in the event that a few tiles are damaged, it's not quite likely that you're going to get such a large impact that you're going to take out a huge section of tile along the vehicle. So it's not likely that you're going to get catastrophic damage if just a handful of tiles are taken off. But you'll also notice on the vehicle, on the nose tip, as well as on the leading edges of the main section of wing, you have these gray areas. And this is not tile material. This is another material called reinforced carbon-carbon, or RCC. And what this was an even more heat-resistant material, because the leading edges of the wings and the nose tip experienced the absolute highest temperatures. This could be almost 4,000 degrees Fahrenheit. So these needed to be absolutely 100% strong, but still reusable and very heat resistant. So they came up with this RCC material. It was very heavy, so you could not make the entire outer skin of the orbiter out of this RCC. But it worked on limited use areas like the nose tip and the wing leading edges. Unfortunately, immediately underneath this was just the aluminum skin of the orbiter. On Columbia's launch on January 16, 2003, debris from the external tank came down about 80 seconds into the flight. It impacted Columbia's left wing in this area here, and it knocked out at least one of these panels, maybe 1.5, 2 panels are knocked out. And what that basically meant was Columbia flew around in space for 2 weeks with a hole in the wing, and they didn't know about it. So when they went back in to re-enter the atmosphere, the reentry gases were just able to get past the thermal protection into the structure of the wing, and it resulted in the loss of the orbiter and the crew. However, assuming that everything is okay, we will fly in like so. We'll fly more or less on this trajectory and this orientation for a while. We'll start to come into the atmosphere, saying we want to enter and land at the Kennedy Space Center. We'll do our re-entry burn, our deorbit burn, over the Indian Ocean, and then we'll come back. We'll start to get some heating effects going around the area of Hawaii, flying from west to east, and then we'll come over the continental United States, and eventually we'll land at the Kennedy Space Center. We've got a lot of speed to lose, though, and no fuel left. So what do? Well, as we're coming through the atmosphere, the shuttle will also bank to the left or to the right while still maintaining its pitch attitude. So what it does is it flies hundreds of miles outside its planned flight path, but what it does by traveling a longer distance is it loses velocity. So it trades the velocity for distance, and it starts to lose speed, and it starts to come down lower into the atmosphere. As the vehicle is traveling lower in the atmosphere now, it's starting to generate more lift. So what it does is it will pitch down around Mach 7 or so, and then it will start to fly more or less like a conventional aircraft. With one notable exception, we have no engines. This thing is a glider. It is a 200-ton glider, meaning that you've done your deorbit burn over the Indian Ocean, you have screamed through the atmosphere at many thousands of miles an hour, and now you're going to land on a runway. You have one chance to do this. You have no engines, and if one little thing doesn't go right, you're going to crash, you're going to end up overshooting, or you're just going to end up ditching. So this has to be right. Basically, space shuttle reentry is an energy management problem of biblical proportions. You have tons of speed. You're almost in orbit when you start out, and you've got to end at 0 on a runway. So all the calculations have to be so that when you run into the atmosphere, that's happening at exactly the right time. That when you make your S turns coming down through reentry, all of that is done at the right time, at the correct attitude, for the correct duration, and you roll out of them in time so that you're still on your projected ground track. At the end of this all, about 100,000 feet or so, you are, get this, you're at 100,000 feet in altitude, you're about 5 minutes from landing. So you're going to go from 100,000 feet to sea level at Kennedy Space Center. In 5 minutes, you are falling at 120 miles an hour or so. There's about a 10,000 foot per minute rate of descent for the most part. It's crazy. It's absolutely crazy. You've got tons of speed, you've got no engines, and these wings are great at hypersonic speed, so above Mach 3, they're fantastic. But as you get down through transonic and subsonic, your lift to drag ratio absolutely plummets. So by the time the space shuttle is on final approach to landing, it's falling at 10,000 feet per minute. It's doing about 350 miles an hour. And it's just absolutely diving for all it's worth. It doesn't have a whole lot of lift. It's diving at a rate about 10 times steeper than a commercial airliner on a normal approach. They will only start pitching up at about 1,500 feet altitude. So they'll start to trade their rate of descent for distance over ground. And they're bleeding off speed like crazy because the aerodynamics of this thing are pretty terrible. In fact, the shuttle was affectionately called a flying brick by many astronauts. Eventually, it will start to pitch up like a normal airliner, and then the landing gear will be dropped at just 300 feet above the deck at about 300 miles an hour. So the landing gear comes down. You're 300 feet off the deck, speed is bleeding off like crazy because now you have got the landing gear out, which effectively is acting like a big parachute out there. You flare the nose up, you come over the runway threshold, main gear touches down at about 220 miles an hour. You roll out for a bit, a drag chute on later flights was deployed out the tail. You rotate the nose down, and then eventually you roll to a stop. So you've gone from orbital speed of about 17,500 miles an hour to 0, starting on the other side of the world. Now you're at the Kennedy Space Center, stopped on a runway, like nothing ever happened. That's pretty cool. No other spacecraft could do something like that. That was something exclusive to the capabilities of the space shuttle, and it was glorious when it all worked well. And I mean, it worked well 133 out of 135 times. So that's a fairly good record. I must say, it's probably the craziest thing that we have ever tried to do with aeronautical engineering. I mean, if Apollo was the pinnacle of overall human achievement by landing on the moon, I would say the space shuttle is the pinnacle of engineering achievement, because even though we're not going to the moon, we're not sending people to other celestial bodies, we're doing things with vehicles that shouldn't be possible. I mean, this thing is about the size of a DC-3, so the DC-3 airliner, but it goes in space, and then it comes back, and it lands, and it's doing it on a runway with no engines. It's a 200-ton glider that's covered in sand, basically, the silica tiles. It's got no engines, the wings don't really do much, and it's got one shot, and it worked absolutely perfectly every time that it ever got to the point where it could be attempted. So it's absolutely incredible to think that the technical achievements that were done with the space shuttle over 30 years, to have it go wrong twice, as sad as it is, it's a pretty remarkable thing. But that's overall the mission profile for your typical space shuttle flight. Now, after all of that pomp and circumstance and a little bit of preaching, what does this look like as a model? There's a lot here. Just be warned. Alright, so now looking at this for the sake of being the model that it is, we've got Endeavour parked over there for the time being, because first let's take a look at the other constituent parts of the shuttle stack. First and foremost, let's take a look at the external tank. This thing, this thing is quite the hefty piece. It is die-cast and plastic. The fore and aft sections of this are done in die-cast, and you can see here the aft dome here, this is die-cast, and the front section here, this is also die-cast. On the actual external tank, this front section, this is the liquid oxygen tank, so all of your super chilled liquid oxygen is here. This center section, this is done in plastic. This is what was called the intertank. This was not full of fuel. This is just structural. It separates the liquid oxygen tank from the aft tank, the larger tank, which was the liquid hydrogen tank. And this here is done in plastic as well. You can see the little shut line through here. And then the aft dome, again, is in die cast. The rear section here of the tank, you can see down here, this is all die cast. This is the struts on either side for mounting the solid rocket boosters. And the boosters interface with the tank with this little tab section here, which is actually spring-loaded. This little center section here, I guess you could almost call it a mortise and tenon joint. This is spring-loaded inside, and the pins on the solid rocket boosters engage with these, and it pushes that pin forward, and then it locks in under spring tension. The forward attach point for the solid rocket booster is here, and this is actually modeled to emulate what it really looked like on the actual vehicle, and it's functional here. The real solids would bolt on to either side of this, top and bottom, from this angle, but on the model, the solids, they actually interface with this through a little hole here. I'm not sure you could see it, but there's a little hole here in this section of that joint, and that's where the solid rocket booster hooks in from the bottom. So when this thing is vertical for display, the solids actually are weight-bearing through the intertank structure here on the ET. So it actually works quite nicely. On the back side of the tank, this is where an umbilical feed line from the service structure from the launch gantry would interface with it. So that's detailed here with just a black blanking panel in plastic. And then just great structural detail on the stringers here through the intertank section. Some rivet and bolt holes through there. It's all very nicely done, very high fidelity. And this tank itself, it's the heaviest portion of the whole stack. It weighs about 2.5, 3 pounds. It's a weighty thing, and it's very nose heavy because this liquid oxygen tank is all done in die cast. The whole texture of it, it's great to feel this thing. It's rough. It's almost like a very fine grit sandpaper, like an 800 or 1000 grit sandpaper. It's abrasive, but not overly so. I think they've done that to try and replicate the texture of the insulation foam that was on these tanks. And the reason why these tanks were orange was because of that insulation. And it was just sprayed on. It was a sprayed on foam insulation, and it would have had a rough texture. So they've done it to do that. It's really cool. The colors on this are great as well. There's a little bit of a color gradient applied to it. It's slightly darker at the nose here, and then it's lighter throughout the base of the tank, going down through the liquid hydrogen tank and then to the aft dome. It's really nice. The struts that hold the orbiter on, this is the forward attached strut for the orbiter. You can see that there is a detent here. The orbiter initially interfaces on the top section, and then it clicks onto it over the second detent there, and it's actually very secure. You could, I wouldn't recommend it, but you could probably suspend the orbiter from the tank and have it hold on just fine. It'd be great. The lower attached struts here, there are holes in the bottom of the orbiter that will show you, and they attach here. These two pins attach into the belly of the orbiter. Nice detail here with the strut itself. Actually, it is weight bearing as well in the model, which is very nice. And then across the top section of the tank, the liquid oxygen feed line coming out from the inner tank, and this goes all the way down to where the orbiter links up, and that is the liquid oxygen feed line for the main engines. So that's nicely done as well. On later shuttle flights, they actually did, they made use of this little fairing on the liquid oxygen feed line. This is where they put the camera on the external tank, right there. So you would get this view. It's focal length on the camera won't work really, but you'd get, you know, view roughly from this angle, but zoomed in a hell of a lot more than that, and just looking down the side of the tank. Pretty cool, and very nice to see all of that detail from this side again. Wonderful. Some electrical lines going down. Very cool. Very, very nice job on the external tank. I think my favorite detail on the tank has got to be the nose cap. Look at that. It comes to a pretty sharp point. It actually is quite sharp. Very nice. Very nice indeed. On the back side you can see a little bit of a vent here on the nose cap. And this is also something that you saw on the launch coverage. Very cool. Very, very cool to have an external tank that you can hold in your hand. It's very nice. Very nice. The next bit of detail, solid rocket boosters. Obviously there are two of them. This is the right solid rocket booster. And again, it looks and feels like you would expect a solid rocket booster to feel. The nose is die cast, and the tail assembly where the nozzle is also die cast. It's die cast from this point here all the way rear. So it's very, very cool. Inside the nozzle, it's powder coated, painted, very nice. The nozzle doesn't gimbal, but it's there. And you can see the little insulation bellows here around the nozzle as well. That would allow it to swivel around. Very cool. Separation, solid rockets here. These would fire in booster separation, so all that is there. Also the motors at the top here to push the booster away from the orbiter during booster sep. That's also there. Here is the mounting post that interfaces with the external tank in the forward section that we showed you. So this little peg goes into that hole on the external tank. And then here is the aft section of the booster, and this is what engages that spring-loaded lock on the external tank to hold the booster in, and then this little strut there goes down and just basically stabilizes the booster. Doesn't really do any weight bearing. But that's all very nicely put together, and again, it looks and it feels like a solid rocket booster. You can see down the side, if we tilt it the other direction, you can see down the side you've got these little decals. They say loaded in case you can't read them. And they go most of the length down the booster. There you go. Loaded, loaded, loaded. So again, it's showing you that it's ready for flight. It's really, really nicely put together. The left SRB, again, it's a mirror image of the right booster, but there it is. It's all nicely done. It's fantastic levels of detail on this thing. Really, it is. So cool. Nozzle on the left SRB, again, same deal. I don't think, there's really not much to see in there. I can't quite get the shadow to work right, but you can see in there, powder coated, some gloss, but that's the nozzle. There's no detailing in terms of ribbing inside the nozzle. It's just a smooth, truncated cone that just terminates about, I don't know, about, let's see, that far. So there it is. But it's cool. It's really cool. And again, it's It's a solid rocket booster. What more do you want to have on your desk? It's a nice thing. It's a really nice thing. And if you're a space enthusiast, you could just look at this all day. Of course, the ultimate piece of resistance in this is the orbiter, and holy God, do we have so much to look at here on Endeavour. It's the second heaviest piece of this. It's extensive die cast. Most of the orbiter is actually die cast. Let's see. The nose section is mostly die cast. Most of the fuselage is die cast. The main body of it, the wings, are all die cast. The leading edges here, the panels here that we talked about, the RCC panels, they're plastic, but the actual structure of the wing is die cast, and you can hear that it's metal. Very, very cool. Just awesome detail all around. You've got great texturing all across the tiles here. You can probably see them. Awesome. Great look at the forward RCS thrusters. These were the reaction control system engines. These were the translational thrusters, so these would fire, and this would be able to push the vehicle backward if they wanted. The rotational thrusters are up here, the three of those. So that's all very nicely put together there. And then, of course, along the sides, you've got the RCS for your yaw axis. Very nice. On the port side, the left side of the vehicle, we've got the ingress-egress hatch. So this is where the crew would enter the vehicle on the launch pad and then exit after landing. They would literally pull up some air stairs next to them, and they would get off just like they were getting off an airliner. You don't have the decal there that says rescue or anything like that, but you do have the yellow bars where that would be. Then down there you've got more decals, and then again you just get awesome texturing all across this thing. It's really great. And then the decals, the American flag, United States, NASA. It's really fantastic. And payload bay door can close down a little bit more, but yeah, very nice. Very, very nice. The rear section there is the OMS pod, the orbital maneuvering engine pod. Go up a little bit. There we go. And of course, the tail, and you get that great texturing all across the entire surface of the orbiter. The white sections, the black sections, it's all got that tile texture. It's fantastic. You also get a little bit of thermal blanket detail as well. Like you can see the panel seams there, where in the white sections in particular, in the upper section of the orbiter, those weren't tiles on the later flights. They figured that these were non-critical areas, so they substituted the tiles with a thermal blanket material that was just a little bit easier to work with, but the same overall idea. And you can see the detail on that. But the tiles are on the black sections and some of the white sections as well. And then, of course, the entire belly of the orbiter is all done in the tiles. And it just looks so absolutely fantastic. Down below, you can see the nose landing gear. That's a rubber tire on that. So that's absolutely correct and looks great. Same thing with the main landing gear down there. Again, actual rubber tires rather. And then you can see the landing gear door with the tile texture on that as well. It's absolutely great. Really, I can't think of too many things to criticize so far about this model. It's it's a fantastic thing, and of course there's more detail to be found underneath. So underneath the orbiter, we've got, of course, the black tiles underneath that we talked about before, but there's your landing gear, obviously deployed right now, but it actually retracts. It doesn't just stick in place. It actually retracts, so there's the nose gear going up and the nose gear doors, which actually close. Same with the main gear. There's a little strut here on both of the gears that actually locks the gear down. So to retract the gear, you've actually got to push that strut in, and then you can retract the landing gear like so. A little bit wonky because I'm on an angle. There we go. There you go. The doors close up. Same thing here. Unlock it, push it up into the wheel well, close the door. It's tremendous detail. And then of course underneath the underside of the orbiter, all the doors closed. Everything is now flush. It's great. Absolutely great detail. Down here, these two hatches, these are representations of the umbilical doors. This is where the orbiter links up with the external tank. And they're not just representations, they actually open up. And don't crucify me, but you need a tool to do this. So very gingerly, you put in a very small flathead screwdriver and just pop them open like so. Very, very gingerly. And then you could use your fingers for the rest, but they swing open like this. So you can get that. But they don't open all the way. That's a problem if you want to put this on the external tank, because obviously there are your mounting holes there. So how do you get around this? Well, these doors are actually on a double hinge. They're hinged so that they swing, but then they are on a detent. You pull them up, and then the doors pop up a little bit, which then allows you to swing them all the way down flush to the belly of the orbiter. And then you can put it on the external tank. It's absolutely wild what they were able to do with this. And again, it's a scale model. It's something that's meant for display. They put that amount of detail into something like this. It's absolutely crazy. We gotta extend the landing gear again to show you the next bit that I want to show you. So again, just a little screwdriver action is needed on the nose gear, and you pull it down, and it locks into place. The main gear, for the most part, you can do this with your fingers. You go in and grab it, and then it locks down. So like so. Yep. Deploy the landing gear. Get it back down. It sits very nicely on the gear as well. Doesn't quite sit level, which is actually authentic. The orbiter did not sit down straight and level when it was landed, so that's cool. And then on the rear, this is really what sets this apart in my view. On the rear, you've got the main engines that we talked about before, the orbital maneuvering engines. But guess what? They gimbal. So you get the main engines. They are mounted here on ball joints, and they can actually swivel around into basically any sort of orientation you wanted, even this very grotesque looking one that you would never really see. But all three main engines, they gimbal around to put them in any sort of position that you really want. The orbital maneuvering engines, they also gimbal, which is really cool. So you can make it look all weird if you really want to. But yeah, it's all absolutely fantastic. The main engine nozzles are in die cast. The orbital maneuvering engines are also in die cast. And they, yeah, they're pretty tight, but they're not that hard to move around. And then, yeah, they stay in position as well. It's absolutely brilliant stuff. Really, more or less during flight, they would be in this position here. When you lost all hydraulic pressure, when you turned off the auxiliary power units, they would, on the ground, everything would droop under its own weight. But yeah, that's really, really cool. And also you can see the texturing of the tiles behind the engines as well. Also what moves on this model here in the rear, the elevons. So you can see the elevons here. They are completely posable. So put them all down to their maximum extent there. So there you go, the elevon's down. The body flap also goes down. So we can move all of that down. So this is everything now fully extended, pitching down. The body flap had most of the pitch authority on the orbiter. The elevons as well. You could, obviously in this configuration, impart some downward pitch as well, but the body flap was really important for control on the orbiter in atmospheric flight. And there it is. It's movable. The rudder as well. It deflects. There you go. Full left rudder, full right rudder. It's absolutely fantastic. And the speed brakes as well. They move on this, and I still have yet to be able to do it because they're so incredibly thin. This rudder splits in half basically, and that's the speed brake. I don't know if I'm feeling quite brave enough to try it, but the speed brakes do come out. It's really cool. Other details that we have on the orbiter: we've got the payload bay doors open again. Make it a little bit easier to do this. The little fuselage on the OMS pods, that comes off on either side, and underneath it allows you to take a look at some of the fuel tank detail going on here. Lots of little tanks here, nitrogen tetroxide and hydrazine, probably some helium there for pressurization. Really cool, really cool. The aft RCS for your roll and pitch control there. Very nice. Very, very nice. And then, of course, you can see some of the structure as well underneath. Really, really, really cool. And it, of course, you get a little bit of an interesting proportion there with that removed on the rear of the orbiter. But really interesting to note that detail there, that they thought to have this removable. It just adds a little something. The underside of that, all in plastic, but there it is, and there's that texturing up close as well. Very cool. Very cool indeed. The last bit of detail, though, that we've got to talk about on the orbiter is the cockpit. Now, the hatch doesn't open or anything like that, and wouldn't do us much good if it did anyway, because, well, that's a really small opening. But we can get into the cockpit on this thing, and the way in which we do that is we carefully start to pry up, and then the whole top section of the orbiter comes off. There is the windshield on Endeavour. There's the orbiter name, and then underneath, there you go. It's the closest to looking out the shuttle's windscreen that I'll ever see. But there it is. Again, done in silver, just like the OMS pods. And the top cockpit windows, and then the overhead windows there. Very cool. Aft section. This would be facing into the cargo bay. So real nice. And then the orbiter looks awfully funny without its top section there, but there you go. And you can see some structural support going on in here, and there is the inside of the cockpit as well. Yep. See your screens there for the glass cockpit. And then only 2 seats here on the flight deck. That's kind of interesting because typically you would see 4 astronauts on the flight deck, if not 5. But yeah, 2 seats there on the flight deck of Endeavour, and then just a really cool view looking at the cockpit there with the display screens and all of that in there. Really cool. But there's more. The space shuttle we mentioned before, it has 2 decks. The airlock in the cargo bay, it was accessible from the lower deck, which was actually called the mid deck, and that's where the crew had most of their living quarters. So the flight deck, the top deck, actually lifts off with a little bit of persuasion. And in a moment there, hopefully we'll get it off. Again, this is very tight tolerances in this, so it's a little tricky at times to get all of this stuff removed, but it is removable. I do trust that you believe me. Almost. Not quite. Not really. It's not really secured with anything. It's just sitting in there under its own tension in terms of fitting quite tightly in its little space there. I need to maneuver this, I think, a little bit more. Oh, there we go. All right, so there's the flight deck, and try to get some light on that for you. There we go. Will you focus? Yep, there you go. So there's the flight deck. two seats, little joysticks in front of them. Cockpit displays, really cool. Some attempts at rendering the panels to the side of the crew. Cool. Some of the displays that would be in the back. Nice. So that's interesting. And then finally, the last bit of hidden detail on the orbiter is the mid-deck. So this is the lowest deck of the space shuttle, and this is where we have 3 additional seats. Typically, there would be, for crews of 7, you'd have 4 on the flight deck at very least. Sometimes you would have 5 on the flight deck, and then you'd have 2 on the mid-deck. But there were a couple different seating configurations that were available on the shuttle, so that's one of them. But yeah, really, really cool just to be able to get mid-deck detail on a model like this. And this is where the crew would have their sleeping arrangements. You can see in the wall there, you've got some cutouts in the wall. The crew, some crew members anyway, could sort of wriggle into those compartments and they would sleep in there in sleeping bags. This section here, that is where the toilet was. So again, you could figure that's about just barely enough size for one normal-sized person to float into. And remember, in microgravity, you're not really hampered as much in terms of your range of motion, so you could do that. And then in the back section of the mid-deck, you can see that circular detail right there. That is the entrance to the airlock that goes to the cargo bay. So there you go. That's how you get outside when you're in space. Really cool. And again, just awesome that you get detail like that on a model. Again, that's the closest I'll ever get to being inside the space shuttle. There you go. My finger is inside the space shuttle. Awesome. It's cool. Really, really cool stuff. And again, I would never have thought to look in there, really. If they didn't bother to put any cockpit detail on this model at all, it would still be brilliant. But there it is, not only the cockpit, but the mid-deck. You can actually see inside the damn space shuttle. It's cool. It's so cool. There's nothing else here that lifts off, but what we have is just tremendous overkill as far as I'm concerned. But it's a real spaceship. It really does look like something you could live in. And, you know, it's nothing great, but it's not terrible either. In case you're wondering how the crew transferred between the flight deck and the mid-deck, there was a ladder which allowed them to access both levels on the ground, but in space, it doesn't matter. So you just float through a little hole in the floor on the flight deck, and you can just barely see it. Lower area frame there. There you go. There's the hole in the flight deck floor. And they just float down through there to the mid-deck and then float back up. Really cool. So decent living space on board shuttle. Still nothing huge. It's still smaller than, you know, the smallest studio apartment, but hey, it's a space shuttle and you're going someplace. It's cool. And I don't think too many astronauts really complained about the accommodations because you're in space. What more could you possibly want? So we'll get the orbiter dressed up again. So our flight deck goes back inside like so. Just sort of, you know, actually takes a little bit of force to pop in there. And you don't want to really put too much stress on the landing gear when you do this, so it helps to lift it up. There you go. And then the outer skin, really, of the orbiter goes back in place. So it slides in under a little detent, and then it just snaps in like so. We'll get the payload bay closed up, like we see here. The other door closes up. We get everything snapped down. The hinges come back into place on both sides. And then we get ourselves a pretty smooth, flush closing of the doors. Orbital maneuvering pod covers go back on. Then on the other side, Snaps in underneath the edge of the payload bay doors on both sides. So that's pretty cool. Our orbiter is now fully reassembled, and now how we put it together for the initial launch configuration as we saw it at the beginning. So we will get the landing gear put back in place. So just as we did before, close up the nose gear, get it stowed properly, close the doors. There we go. The main gear, we unlock them, push them forward, close the doors, leave the umbilical doors open. That's important for assembly. You cannot assemble it if the umbilical doors are closed, so that's fine. We will zero out the angle of attack on our elevons, and our body flap we'll just double check. Our rudder, we'll make sure the rudder is as centered as we can make it, and we'll just leave the orbiter aside for the moment. The external tank is the first part of the assembly that we put together. So the solid rocket boosters go on the sides of the tank. We'll start off with the right solid rocket booster. So there we go. You can see how this works. The little pin on the side of the booster goes into the hole at the forward attach point. So there you go. You can see the interface there, and they go in like so. The rear strut, there we are. So that goes in like that, and then basically you just push inboard and it locks into place. I'll show you that a bit better. Get everything back in. Lower strut goes in, and then push it inboard and it locks into place. So that's now pretty solid. The left booster is exactly the same process. So again, just putting it together like so. Oh, missed it. It's like threading a needle a little bit. And I can do this. There we go. Line up the strut down at the bottom, push it inboard, and almost. Sometimes it takes a couple of tries, and now that's locked in. So there's your external tank and SRBs, and they're pretty solid in there. A little bit of movement, not much, and there you go. Last bit, of course, the orbiter goes on. And it's easier to assemble it horizontally like this. Line up the umbilical doors into the ET umbilicals there. There you go. And then the forward strut goes into the hole at the bottom of the nose. It finds its way pretty nicely. That's the first detent. And then just press down. Don't worry about it. You're not going to hurt anything. There you go. So the last bit here, get it onto the pad, and it's a little bit cumbersome to get it lined up properly on the display stand, but as long as you come in perfectly vertical, it's not too hard, and then it just kind of falls into place. I kind of missed it a little bit. You can see that it's a little wobbly. You gotta get it just so that both boosters are on the support points. But once they are there, and it's still not quite there, is it? Good enough for government work. Standing a little bit crooked. Yeah, I just want to show you that it's a little bit cumbersome. But ultimately, if you're willing to be a glutton for punishment, eventually you will find the point where it is happiest. There it is. It falls into place by itself. Boom. So now it's sitting nice and snug. The boosters are secure. The orbiter is really secure. Like, I've really got to yank it to get it off of there. And it's stable. And the last thing to do flip the lights on, and there you go. You've got yourself one Space Shuttle Endeavour in 1/144th scale, ready for display, and it's a really, really, really cool looking piece. And there it is, moving you up the stack. Absolutely awesome. So there you go. That is the Space Shuttle Endeavour in 1/144th scale by Bandai. It's an absolutely incredible model, and it's taken the better part of 2 hours to show it to you, and I am terribly sorry to those of you who have bothered to stick around this long, because wow, there's just a lot here, and the space shuttle itself is a really complicated thing, and I didn't feel like it was something that I could just gloss over. So there it is, you got the whole thing, nitty gritty, even the personal opinion side of it. But it's really, really cool, and it looks so cool with the lighting there. Unfortunately, I think Bandai missed an opportunity with their Saturn V model to include lighting on this, because that display base didn't have any sort of lighting, and I was actually really surprised to see it on this. But it's a cool thing, and yeah, I'm going to turn the lights out here, and you can get the full effect of having it under the spotlight. I've got my my own little flashlight here just so I don't bump into anything, but I'll shut my light off. And there you go. The only light now in the room is from the display. And it looks really, really, really cool. And just the way the lights are, the shadow falls right over the cockpit. But it's a pretty dramatic sort of view. Zooming out a little bit, you can get the full effect. But it's really, really nice. You can move the lights around if you want a little bit. So they swivel 90 degrees from left to right, and then you can angle the spotlights in basically any way you want, about 70 degrees or so up and down. But yeah, it's a cool looking thing, and yeah, there it is. Space Shuttle Endeavour under the lights. It's a really, really great piece. It's definitely something that I think a lot of people who didn't jump on it when they went into production, I think it's something that they're going to regret, because this is a cool vehicle. And in terms of being a model, I mean, come on. It's the coolest thing I've seen in many years, and I've seen quite a few cool things because I've been collecting models for a long time, but this takes the cake, 100%. This is better, I think, than the Saturn V, simply because of how cool it is. You can hold this in your hands and play with it, sort of. The Saturn V, it's big and it's difficult to maneuver around, but it's cool. It's really cool. And I'm just rambling a bit now because it is so cool, but there it is. Space Shuttle Endeavour by Bandai, 1/144th scale. It's an absolutely beautiful piece. If you find one for, less than $3,000, it's a bargain at this point. It's brilliant. It's absolutely marvelous. And I don't think it's going to be surpassed anytime soon by anything else. Unless Bandai decides to make, I don't know, the Saturn 1B or the Titan II or the Mercury Atlas or whatever. Please, Bandai, make more space vehicles. You're great at it. But I hope you all very much enjoyed this one. I very much enjoyed making this whole extravaganza for you. FerrariMan601 saying thank you so very much for persevering with me, if you have decided to persevere with me for this long. And of course, we will see you soon, probably with more terrestrial things to come.